everybody for this sixth installment of the Code of the Month. I'm Gunnar Berti from the CASTIEL project, and we had the joy to have as guest today Niklas Jansson from KTH. He's a researcher at KTH and coordinates the CEEC Center of Excellence in High Performance Computing. Niklas will present us some details on the code NEKO, which is this high resolution CFD code based on spectral elements, and he will tell us why this type of code is particularly suitable for the highest end of current HPC systems. So, Niklas, the floor is yours.
Thank you, Guntram. I should try to get the slides are showing. I can also turn on the camera as well to say hello. So again, thank you, Guntram, for the introduction. So yes, I'm Niklas. I'm from PDC, the HPC Center at KTH. So I'm going to present our work on developing this new framework that we call NEKO. So we try to make it modern, portable, so that we can target current and upcoming computer architecture as well. So as a motivation, so we are into computational fluid dynamics. And this is actually a very interesting topic when it comes to this theme of exascale and large-scale computing. Not only is it important for the societal point of view, because it's said that, for example, 10% of the energies used in the world is spent overcoming turbulent friction, be that pushing fluids through pipes or pushing an aircraft through the air. The problem is that in order to make better designs in this, you need to do very detailed simulation that are very, very costly. And this has been used several times. For example, Praise used it back in the day to motivate petascale computing in Europe, but also NASA has written a lot of papers and roadmaps on arguing why we need to have large-scale computes for CFDs. Another thing is that in CFD, compared to other scientific fields, for example, MD simulations, we don't have a sort of fixed problem size given by what the problem we are solving. We don't have a physical set of molecules, for example. So in CFD, we can always add high resolution, add more grid points, and we get more science out of the simulations. And that makes it an area with a clear need and also great potential to reach exascale. So exascale in itself, if you take a step back and think about it, what it actually means, it not only means a fast computer, it also means a very large computer. And if you want to run on a very large computer, that means that you need to have a very unreasonable large problem size so that you can fill the entire machine. Or the more difficult way is that you try to make significant improvement to your current methods, such that you can scale today's problem on a much larger machine. Just to illustrate how bad this can be. So back in the day, I used to work at Riken. We ran on K-Computer, the red machine up there to the right. So we filled the entire machine running one simulation for a finite volume LES of a full car. That needed around 100 billion grid points to run efficiently. So K-Computer was the fastest machine in the world, but it was only 10 petaflop, more than 500,000 cores. And if you make a very naive flop-to-flop comparison, 10 petaflop is basically what we have now in half a cabinet down in the basement at PDC in our Cray. And then you can get nightmares when you think about what kind of problem size you need then to fill the 380-ish petaflop LUMI if you do this comparison. So of course, this will not fly. We cannot just artificially inflate our problem size to fit the machines. We need to do some work on the numerics and algorithms. And the solution here, it has been known even for CPU codes for a long time. High order method is the way to go forward. They will give a lot of nice numerical properties, but also they are much better suited for modern hardware, which in the current day and age means accelerators. So just one more thing, introduction and motivation here is that accelerator, of course, is very fast, but they have another problem. So in a figure down to the right, we see the performance of one important kernel in our simulation, and the red line there is an NVIDIA A100, and the red line is the AMD EPYC 7742 CPU, and the green one is the NVIDIA A100. So typically for accelerators, we see that they are very fast when they have a lot of data to work with. So on the x-axis here is the number of elements. And that will then kind of contradicts what I said before, because I said we want to scale out our current problem. So it means that we are trying to target the difficult region to the left, where the accelerator might not be as happy as it is with a lot of data. So keep that in mind, and going forward, if we look at what kind of machine we have around these days, we can go and look at the top 100 list from November. And we see that we have a big mix of both accelerated and CPU machines. I mean, Frontier accelerated. So 1 and 2 is accelerators, 3 as well. Number 4 is still CPU. And then we have the European Lumi and Leonardo both having accelerators. So it means that if we want to have a portable CFD code, we need to be able to do two things. We need to run on GPUs and CPUs efficiently. And we also need to support various hardware vendors. Because if you look at the list, we see we have everything from AMD GPUs, NVIDIA GPUs, to Intel GPUs as well. So it put a lot of requirements on the code that you are using. Because if you're in CFD, you really want to target the top tier of this list in order to be able to run. You don't want to say no to a machine. So we had this problem in the past at KTH. We were using a code called NEK 5000 that has been giving us tremendous amount of science. It was written in Fortran 77, and now we realized that the future world would then be accelerator based. We needed to find a solution moving forward. So we had a lot of discussion if we're going to try to retrofit accelerator support to NEK 5000 by adding OpenACC or OpenMP pragmas. But after some trials, we realized that we don't get the performance out of it that we need. And we still didn't have a good option for certain. We saw different performance variation between, for example, AMD and NVIDIA and also Intel going with this directives approach. So we said we needed something new. And then we went back to the drawing board and said, are we doing the right numerics as a start if we're even gonna go with a new code? So we wanted high order, and high order at KTH means spectral elements. So it essentially is finite elements, but with a high order, so that's a lot of grid points. So basically you have your, in our case, hexahedral elements, as you see up here on the right. And then each of these elements are then filled with a lot of degrees of freedom, so that you get a lot of compute per element. And we know this is very efficient to implement even on CPUs, because in the end you get down to this level 3 kind of blast operation. To make it scalable, you have to realize that it's too expensive to assemble your sparse matrices. So everything is done matrix free. And then you need to pay a lot of attention on tuning certain communication kernels between the element that is referred to as scatter. So the two key points here to make spectral elements efficient, you need to have these tensor product operations, which becomes when you assemble these elements. They have to be fast. And secondly, you need to do the scatter operation between the elements fast as well. So compared to other codes like high order finite volumes, our communication stencil between elements in spectral elements is only of a unit depth, which means that we only need to communicate a very small fraction compared to high order finite volume codes, for example, which has a very wide communication stencil due to all the ghost points. So we know that the numerics is good, but we need a new code. So that's why we have created this new portable spectral element framework called NEKO. So currently it's limited to Navier-Stokes with some additional scalar equations. So we can do temperature, for example. But we have put a lot of focus on getting the matrix-free formulation, these small tensor products fast on various architectures. And also the gather scatter operation is running at peak efficiency. So we're sharing a lot of the methods from NEK 5000 and related codes, but we have departed from Fortran 77 and rewrote everything into modern Fortran 2008. I should not say rewrote, it's a new code, but the design is completely different. So we are designing the entire solver as sort of a solver stack, as you see in the middle. So we have like a case and a computational mesh. These gray boxes are always sort of the same, but the red pinkish boxes there are completely virtual types. So when we create, for example, a matrix vector product AX, which is a key kernel in spectral element, the solver will always operate on this red pinkish box. But once we have started, everything is run. It's actually initiated with a hardware tuned version, which is this green boxes down here. So it means that the person developing the solver is always working on the abstract level, but at runtime, of course, this is instantiated into the tuned one for a certain backend. So this is the way that NEKO supports various hardware backends, going from CPU, GPUs down to very exotic vector CPUs and even FPGAs. And how we deal with accelerators from Fortran, that's via our own device abstraction layer that I will talk about a bit in the next slide. But if we think about performance here, and we look at the slide to the right, this is NEKO running a Telegreen Vortex case on a set of different European machines. I don't expect you to be able to read maybe the labels, but I can add some legends into the figures. So we see that we have several CPU results to the right. In the middle, we have one vector machine. And then to the left, we have a lot of various GPU clusters. And on the x-axis here, it's processing elements. So that means a CPU core, a vector core, or one logical GPU. So not dwelling too much into the scalability of this plot of the performance, the key take home from this one is that for the scientist, this is the same Fortran file describing the Telegreen Vortex case. And then NEKO automatically will then run on the backend it has been compiled for. So that's great for the scientist, but of course, create a bit of a nightmare for us developers. So that this has also morphed into an exercise into modern software engineering. We do a lot of testing using PF unit, verification, validation using Reframe, and then rely on modern deployment tools like SPAC. So you can easily log into most of this machine on the top 6 there, and then you have to SPAC install NEKO plus some options, for example, CUDA, and then you have NEKO installed and up and running on Leonardo, for example. And I just mentioned that we're a bit too happy about our domain name. We actually managed to get neko.cfd as our homepage. So if you're interested, you can find more information using that simple address. So let's dive into a bit more technical details here. So the device abstraction layer I mentioned, we did some tests using directives. We realized fairly quickly that this will not give the performance that we were after. So we realized that we need to kind of replicate what we need from the accelerate APIs. So we have inside NEKO that we are writing a lot of C interfaces so that Fortran can call relevant part of the APIs. So for example, we are replicating the HIP API. So you can call HIP malloc, for example, to get some memory allocated on an AMD device. Same for CUDA and same for OpenCL as well. So how it works is then that we have this layer is just prefixed with device. For example, device alloc, as you see down to the right, will then fall down to CUDA malloc, HIP malloc, or CL create buffer, depending on which backend you have compiled NEKO for. So that's how we interact with the device on the memory management, but inside the code itself, we have a lot of derived types, for example, describing a flow field. And then you always have a normal Fortran allocatable array for the CPU data, but you also have a C pointer for possible allocations on the device. Which means that we always can associate between CPU and GPU data for the same type. And to be able to find this mapping deep down in our call tree, when we might have actually done just this allocatable array left, we also have a hash table that are associating these two addresses so that we associate the CPU address with device address as well. And some of you then might think that this is exactly what OpenMP or OpenACC provides for you. Yes, that is true. But we realized early on that when we tried this, it was so many bugs, especially since we relying a lot of object orientation, that we got a lot of implicit memory copies, which of course hopefully will be fixed in OpenMP in the future, but we couldn't really wait for that, so we decided to roll our own interface that we have full control of. So that is sort of covering the memory management part. When it comes to launching kernels on the device itself, they are also launched from this object hierarchy. So for example, one of these green boxes there might be a GPU or a CUDA. So that would then go into a Fortran code that would then call a C++ or C wrapper function for the supported backend. And this would then be templated CUDA heap code or heavily pre-processed macro C code for the OpenCL backend, such that it can nail down runtime parameters like polynomial orders or certain kernel sizes for the meshes. It has turned out to be very important to actually have different code paths for different vendors, because even CUDA and HIP is very similar. We have to actually pick, given a polynomial order and a problem size, different kernel strategies on the different vendor cards to get the peak performance. So every time we launch a new kernel, we actually do a check if we have found the fastest kernel. If not, we run a test suite, and then we store the fastest polynomial order for our current problem during runtime. And it's important that this also supports various polynomial orders, because we're running what's called like a multi-grid based on the order. So we need to actually be able to run fast on a range of different polynomial orders for our problems. So this is more on the how we interface with the GPU, and also how we make sure that the GPU kernels are fast. The next thing that we need to have fast is also communication. And here we learned a lot from working with the NEKO Essex Aurora vector card, which really needs long vectors to operate efficiently. So compared to other spectral element-based code, we are using what's called topology-aware optimization for this, because scattering itself is a lot of indirect addressing, which is mostly non-injective, which means that it cannot really be vectorized. And it comes because you need to basically go from a limited address range to a large address range that you cannot represent on one node. So you need to do this a lot of lookup in various tables. So from a sort of a geometric point of view, if we have these elements here, we realize that all these red points, which are on the facet between elements, they will only have a single neighbor. So if you then need to do this gather scatter operation on the red points, they will always be injective and then vectorizable. So they will be able to operate very fast. Then we have some sad points, the green ones, which will be corners or edges in 3D. And they can have arbitrary number of neighbors, since we sort of have an unstructured mesh of these hexahedrons. So of course, these cannot be made directly injective, so we cannot vectorize them as good as the other ones. But luckily, the number of green points are much less than the red points. So the way we do this is that we are sorting all the red points and put them last in a long vector. So the way we're numbering when we're numbering these points internally. And then the green points we put first, and then we identify which ones are corresponding to each other, so that we have smaller blocks that will be vectorized, but short vector lengths there as well. So this gave a lot of performance on the vector card, and that was actually very good prior work when we moved this to the GPU later on, because it was directly applicable, and the GPU was quite fast with this setup as well. Another thing that I want to stress when it comes to performance of the code is also the way we're doing communication. And it's crucial here that we're overlapping communication and computation as standard in these kind of codes. Because we also have this gather scatter internally between elements, internally inside a node. So we have two kinds of gather scatter. One is the internal between the elements, because it's matrix free, and the other one is external with another node as well. So we're doing overlapping with the internal. So we start doing one operation for the external, and then we overlap when the messages are in flight. We're doing the local internal node gather scatter operation, which is without MPI. And we're not only doing overlapping, we're also using device-aware MPI. So it's very important, especially for example, Lumi, that you're using device over MPI, which means that you communicate directly from the device memory without having to copy it into the CPU itself. Because on the nodes like Lumi, this is our machine at PDC, the network goes directly into GPU. So we don't want that extra round trip going to CPU memory and then shuttling it back out via the GPU again. And the difference can be seen in this plot that was done some time ago, but basically we see the difference between the blue and the orange line here is really the performance diff between doing that extra copy or going directly out from the GPU to the network. Another thing is that we are really chasing latency here because, as I said in the beginning, we want to scale out very small problems to a big machine. So we also do all this asynchronously. So we are launching pack-unpack kernels for this scatter operation in different streams. So basically one for each physical neighbor, such that we don't have to wait for the late arrival from a node. So as soon as we get a message, we can start an unpack or pack operation in a stream as well. But it turns out that it's not clear from the start, given a machine, given a problem, if all the pack or all the unpack operations should be asynchronous, or one should have synchronous or combinations with asynchronous operations for certain neighbors. So this is something that we also do at runtime by testing when you start the simulation to pick the fastest combination for a given problem, polynomial order, and now also machine topology and job allocation. So with this sort of technical insight into NEKO, let's go into what we actually have used it for. So we have done some timely simulation. This was one of the watershed simulation actually for NEKO that we looked into what's called a Flettner rotor. So you have like a ship and you have a cylinder on top that is rotating, and that will act as a wind sail to reduce fuel consumption and energy use of the ship. For NEKO itself, this was the simulation that we realized that we can get results in less than 2 days on our GPU machine, DARDL-G, compared to running more than 2 weeks on the CPU partition on that machine, or even more if you factor in queue time as well. And this was the point when we realized that we need to currently CFD will be on accelerators no matter what. So we really need to tune this a lot. So what we use this for is that we have studied a lot of different rotation speeds alpha for the cylinder and see how the weight goes from a stationary to a bit more curved, which actually is an indication of getting this lift that will increase and act as a wind sail. And also we have compared this against experiment, and it's very happy to see that it actually are pretty good when it comes to this lift generation compared to wind tunnel experiments for a similar setup as well. So with good performance, interesting physics, we wanted to see if we can do a bit more challenging, and we went into what is called turbulent thermal convection. So what this means is that you have application for this in everything from ship cooling to the convection inside the Earth's mantle and the sun. And what we studied here is a very canonical case called Rayleigh-Bénard. So basically you have a cylinder and you heat it at the bottom and you cool it at the top. And then you get convection cells going up and down like that. You can think of it as a simplified or very expensive lava lamp that you're running. But this canonical problem actually has a very fundamental open question, which is called the ultimate regime. And it relates to the scaling of the Nusselt number to what's called the Rayleigh number, which is related to buoyancy. This is a long-standing open issue in turbulence, going back to the 60s. The thing is that we cannot perform controlled experiments at this high Rayleigh number, more than 10 to the 15. So the only way to try to resolve this open debate is to do simulations. And the challenges for this is that simulation will have a very high cost because the resolution relates to this Rayleigh number to the 10 to the power of 9 divided by 8. So it's going to be very large problems that you have to run. The second problem is that you need good numerical methods and you have to be able to capture and track small scales over a long time period. because you need to do also long time integration to get steady state statistics, so very long simulations. And of course, if you want to study this, if the problem size is large, you're going to create a lot of data that you need to handle in a certain way. If that was not enough, what is sort of probably given is that, of course, this requires an efficient implementation of modern hardware so that you can try to address these grand challenge problems. So we felt that we might be onto something with NEKO, so we assembled a team, a European team, across various institutions and universities with various background, filling in the missing gaps in NEKO to address these things. And first, we can look at the data management part. So this was based on a previous European project called Admire. So inside there, they have looked into lossy compression methods, where you basically discard the modes of the flow that you're not interested in. And then you do lossless compression of the lossy compressed data to get the data reduction down to 97% around, and with a relative error of 2.5%. And if that's not enough, you can of course tune certain parameters to get within your error tolerance as well. But if you look at the figure down to the left, eyeball norm, it looks pretty okay. But of course, statistics might be in a different ballpark. From a technical point of view, we needed to scale this. So what has been done is that we have a hybrid data compression setup. So NEKO is computing time steps, and then we need to save data. And then we do the lossy compression on the GPU. And once the GPU is done with the lossy compression, it will stream the data over to the CPU, which means that then the GPU is actually free of doing more work. So it continues creating time step, while the CPU is then doing the lossless compression and then write that to disk. So we're overlapping part of the I/O such that we can always make progress computing more time steps. So we are reducing I/O costs with this, and also reducing data size because we have this good compression scheme. So that was very good. Next thing we needed was to make sure that we can scale. So looking at the performance baseline, NEKO was part of the LumiG pilot. So there we actually had run some full machine performance tests in the past. So we were looking at a mesh size of 100 million elements with 7th order polynomial. It's a lot of data. So if you want to understand just one snapshot for this kind of problem size is 1.5 terabyte. If you want to save it to disk for one time snapshot. But more interesting, the performance from that when we ran the numbers was that during that time, we managed to get 80% parallel efficiency, going from 20, 40 to 80% of the entire machine, as you see on the plot to the right. So just to be perfectly clear, this is what is called strong scaling. So we keep the problem size fixed. So at 4,000, it's 100 million. At 16,000 GCDs, it's also 100 million elements for the problem size in total. So it really shows that we can retain 80% parallel efficiency going up to basically the entire Lumi machine with the code. This is, of course, a very good result, but we were a bit reluctant. We really wanted to close this gap such that we can then potentially scale even further on bigger machines like Frontier. So we went back looking at the numerics. What we do in every time step is that we're basically solving 4 sets of linear systems. We are solving 3 velocity components, 1 for each direction. That's done with a conjugate gradient method using what's called a Bloch-Jacobi preconditioner. This is very fast, both numerically and also very scalable. So that is very difficult to improve. The next thing is the pressure solver, which is using a GMRS method with an additive overlapping Schwartz preconditioner. This is, of course, the expensive part. Pressure is always expensive. So you need a very efficient preconditioner, and this additive overlapping Schwartz preconditioner is very efficient. But it might have some implication on like GPUs, for example. So just to give you an illustration, here's a sketch of the preconditioner. It has 2 components. The right part is basically just a fast diagonalization method. We know how to make this very fast. And the left part is more or less that you solve a finite element problem on linear element. So as I hinted, on a GPU, we know this is scalable. And we're using pipeline conjugate gradient solvers for this coarse grid problem on linear elements. And we fix it a set of maximum iteration so that we don't solve it completely. Yes, because the preconditioner, we just do 5 or 10 steps, and then we continue inside the preconditioner cycle. The problem is, as I hinted, is that on linear elements, we don't have enough data to keep the GPU busy. And that can also be looked if you look at a trace from a GPU. At the top line here, that is the GPU activity, and we see it's very fast. So FTM here is the right part of the preconditioner. And then suddenly we hit the coarse grid solver, and it becomes very sad and a lot of small kernels with little work. And this is directly related to this linear problem that doesn't have enough data to keep the GPU busy. So you have to think of the GPU as a bucket of water. You need to keep it at full, otherwise it will not behave good. So we went out and tried to solve this, and we'll start looking at the preconditioner, and we realized that, well, we're not exploiting all the task parallelism that we have in this preconditioner. Since it's additive, it can be done independently. So what we do is that we launch the left and the right part of the preconditioner in parallel on the device. So we create OpenMP regions and different threads, one thread for each left and right part, and then they will inject work into a separate stream on the GPU to increase utilization. And it's important then that this also becomes an exercise in playing around with priorities, because you need to schedule work on the GPU such that the critical path of the preconditioner always make progress. And this is something that we are still exploring and tuning to this day. So does it work? Well, again, we look at the trace, and now we see the GPU activity is just constant 100%, which is exactly what we want. And in practice, what has happened is what you expect. FDM is the right part, what you see here, and this funny looking thing with not so much work is happening right below it. So in the end, we managed to overlap the left and right part of the preconditioner. And performance-wise, we just have to increase the precondition time slightly, but overall, the GPU will actually solve everything much faster as well, because we always use, we maximize the GPU utilization. So of course, we wanted to try this. So we managed to get access on the full Lumi in March, April last year. And April last year, we also were very lucky getting pre-production access to Leonardo. Basically after they just turn on the power and letting people on. So we had a case around 100 million elements, 7-order polynomials, and a really number 10 to the 15. And this should be seen as a pre-study for a current extreme scale allocation that we have on Lumi to study this turbulent convection as well. So it was crucial that performance now was actually good, better than 80% efficiency. So again, we looked at strong scalability. We placed one MPI rank per GPU. So that means one GCD on AMD or one per device on NVIDIA. And then we ran the test on both machines, and we saw this. So a bit unexpectedly, we managed to close the gap from 80% down to close to 99 or perfect efficiency for the entire machine. That's of course excellent. More interestingly is that we managed to reduce the number of elements we need per GPU to run efficiently. So on the pre-study on Lumi, we need around 15 or 10,000 elements per GPU to run at 80% efficiency. Now we can get it down to 7,000 elements per GPU and get them close to 100% efficiency at scale. And this really means that we can then scale out at larger scale and be that efficient. And most of these things are mainly due to this new overlap preconditioner and how we actually managed to tune it based on from the numerics and the hardware that we took. Some people that we worked with were a bit amazed about this and started to say, yeah, but there might be some strange transients in the time stepping. But that's why we also have the error bars here. And that's because that's the 99% confidence interval here. And we see that the data checks out. And this was the basis for, we were actually nominated for Gordon Bell last year. Sadly, we didn't win, but it was very nice that finally we have enough good machines in Europe such that we can start to be a serious contender for this prize on the international scene. And that sort of sums up everything. So the take-home message is that you probably need high order methods or similar techniques that are good for the hardware. Other thing is that the heterogeneous landscape that we have now, not only CPU, GPU, but also different vendors, is kind of a nightmare. So if you're working on codes, you need to find a good level of abstraction, and you should not be afraid of mix the best languages and program models that you find. So not be too agnostic that it has to be this method. And of course, it's very important, and I cannot stress it enough, to use good software engineering approaches to ensure portability and also performance portability. And just illustration of the success of this is this task, decomposed overlap pressure precondition that we have now, that really managed to close the gap from 80 down to 100% on the full Lumi machine. So before we close, this has been supported by both Swedish projects, CEEC, and the Swedish Research Council, and a lot of European projects, CEEC, of course, as coordinator, I need to mention that, but also DeepC, Accelerate, and Admire, and of course, EuroHPC, not only providing the good machines, but also supporting some of these projects. And then, of course, a big thank you to all the good people at Center NEKO for Leonardo, and CEEC also providing access to Lumi and helping us with problems. So with that, I thank you for attention. I'm happy to take any questions.